Hello! We are starting the second part of the course on strategic games. We will start with a famous example called Prisoner's Dilemma and briefly discuss a few of the main concepts in strategic games. For Prisoner's Dilemma, the story goes there are two suspects of a crime. Each of them could either confess or keep quiet. If both of them keep quiet, then there is not enough evidence for a conviction, so they both get a short prison term. If one confesses but the other doesn't, then the confession is used to convict the other. So the one who confesses gets a reward and is freed, while the other gets a long prison term. However, if both of them confess, then they both go to prison for a long time. Now, the story doesn't make much sense to me, so instead, I learned about Prisoner's Dilemma through game shows with a terrible endgame. Suppose you see two players work together as a team and won $10,000. But that's not the end. They each need to secretly make a final decision to either share or steal. If both of them pick share, then they each win $5,000. If one of them picks steal while the other one picks share, then the one who picks steal gets all $10,000 while the other gets nothing. If both of them pick steal, then the prize money is gone and they both go home with a small consolation prize worth $10, say. This is an example of a strategic game. And the question is, how should the players behave in this game? The idea is that the benefit that a player receives is dependent not only on their own decision, but also on the decisions of the other players. So let's define what a strategic game is. A strategic game is defined by specifying a set N of players, and for each player I, there is a set of possible strategies Si to play from. And each player has a utility function UI that maps the set of all possible strategies from all players to real numbers. This is a benefit that player I receives based on the strategies that all the players have played. With Prisoner's Dilemma above, there are two strategies for both players. So S1 is equal to S2, which is equal to the set, share, or steal. Taking some samples of the utility functions, the utility for player 1 when both players pick share is 5,000. And the utility for player 2 when player 1 chooses steal and player 2 chooses share is 0. We can also summarize the utility functions in a payoff table. In this 2x2 table, the strategies for player 1 are listed on the left, and the strategies for player 2 are listed on top. And each cell records the utilities of player 1 and player 2 in this order, given the strategies played in that row for player 1 and that column for player 2. So if player 1 steals and player 2 shares, then player 1 gets 10k and player 2 gets 0. There are a few assumptions that we will make about strategic games. First, all players are rational and selfish. That means that they want to maximize their own utility. Next, all players have knowledge of all game parameters, including the assumption that all players are rational and selfish. The third assumption is that all players will move simultaneously, so they will pick their strategies at the same time. And finally, player I plays a strategy Si from its own set of strategies, capital Si. This forms a strategy profile, which is a vector S containing the strategies played by each player. And player I earns the utility that is UI of S. Now, given a strategic game, what are we looking for? There are many answers to that, and one of the answers is we want to know how are the players expected to behave. What will they choose to maximize their own utility? So let's go back to Prisoner's Dilemma and see what would a rational and selfish player choose to play. If you have not seen this problem before this lecture, then take a few moments to think about which choice would make the most sense. We can think about it by breaking into two cases. If you know that the other player chooses share, then choosing share yourself gives you 5k, but choosing steal gives yourself 10k, so steal is a better choice. On the other hand, if you know that the other player chooses steal, then choosing share gives you 0, while choosing steal gives you 10, so steal is also better. In both cases, it is better to steal than to share, so we expect both players to choose steal. This is an example of a strictly dominating strategy, which means that regardless of how the other players behave, this strategy gives you the best utility over all other possible strategies that you have. So if a strictly dominating strategy exists, then we will expect the players to play it. In this case, playing a strictly dominating strategy, which is steal for both, yields very little benefit. They could get more if there is some cooperation, if both of them share. So even though we expect that the strictly dominating strategy is played, it might not have the best social welfare, which is the overall utility of the players. But in the context of strategic games, we still expect players to make this selfish choice that gives you less benefit. Now, Prisoner's Dilemma has this special property that it has a strictly dominating strategy. But there are many other games with no strictly dominating strategies. Take a look at this example called Bach or Stravinsky. In this game, two players want to go to a concert. Player 1 likes Bach, and player 2 likes Stravinsky, but they both prefer to be with each other. So the utility can be found in this payoff table. If both players go to a Bach concert, then player 1 gets a higher utility than player 2, but both utilities are positive. We have something similar if both of them choose to go to a Stravinsky concert. But if they choose different concerts, then their utilities are both 0. Now, if you are wondering why we had chosen Bach and Stravinsky, that is because this game was originally the battle of the sexes, where a couple is trying to decide to go to a baseball game or an opera. And eventually, the game theorists decided to keep the same initials and made it more classy. Now looking at the payoff table, it should be easy to see that no strictly dominating strategy exists for either player. So, what do we expect to happen in this case? One possible answer is to find a strategy profile where no player is incentivized to switch to a different strategy. So then it is a steady state. For example, if both players choose Bach, then there is no reason for one player to switch their strategy to Stravinsky, which gives them utility 0. We have a similar case if both of them choose Stravinsky. So these are steady states, which we call Nash equilibria. And these are strategy profiles where no player is incentivized to change their strategy. Now, Nash equilibrium is named after the mathematician John Nash in the 1950s. He won a Nobel Prize in economics for his contribution to economic game theory. Nash equilibrium is an important concept in game theory, and we will formally define this term later. But a Nash equilibrium might not exist in a strategic game, at least not in the way we play it so far. Let's look at another example. We look at the classic rock, paper, scissors as a strategic game. Hopefully, you know how to play it. Each player simultaneously chooses one of three options: rock, paper, or scissors. Rock beats scissors, scissors beats paper, and paper beats rock. We will say that a player's utility is 1 if they win, -1 if they lose, and 0 if they tie. And this is the payoff table for rock, paper, scissors. Now, this game does not have any strictly dominating strategy. And if you look at this payoff table, none of the 9 strategy profiles here are Nash equilibria. Can you give a simple reason why none of them is a Nash equilibrium? Well, regardless of what they play, someone is incentivized to switch their strategy so that they win. Say they play rock and paper, then the player who played rock would want to switch to scissors instead so that they win. So how would we expect players to play this game? What is the best strategy for rock, paper, scissors? And the answer is you play randomly. You pick a strategy with probability 1/3. And this is called a mixed strategy. This means that you are playing your strategies over some probability distribution. In this case, if both players play each of their strategies with probability 1/3, this is also a Nash equilibrium, meaning there is no incentive for any player to change to a different probability distribution. And you can think about why that is. Now, a famous theorem from Nash says that every strategic game with finite number of strategies has a Nash equilibrium, which could be a mixed strategy. And we will see a sketch proof of this later. So that is our brief introduction to some of the main ideas in strategic games. In the next lecture, we'll discuss the formal definitions of Nash equilibrium and some related concepts.